So now that we've seen where this formula comes from, and we've seen the criteria for determining whether or not a given scenario qualifies as a binomial distribution where we can use a formula, we're ready to look at some examples. And before we start in on that, I did want to go over the formula again really quickly because there's multiple parts here, and you really need to be clear on what each of them is. So first, remember we're talking about a scenario where you're looking at a certain number of samples, a certain number of people. Some of them are successful, some of them are not. And you want to know the probability of getting a certain number of successes out of that number of trials, right? So N is the number of trials, right? That's the number of samples, the number of patients, or whatever it is we're talking about that we're looking at. X is the number of those that are successful. That's the number that have an adverse reaction or are defective. P is the probability of success, and Q is the probability of failure. Remember that because there are only two options, right, only two possible outcomes, Q is always going to be equal to 1 minus P. Okay, so with all that said, let's go ahead and look at our first example here. All right, we have an engineering situation. They've got a new manufacturing process, and they've determined that the probability of a part being defective is 0.1. And we want to find the probability that 3 randomly selected parts have exactly 2 defectives. Okay, so you see what I've done here, right? This is how I approach these problems. First, we can kind of quickly confirm this is a binomial distribution situation. There are only 2 possible outcomes, and all of the outcomes are independent. Whether or not part 1 is defective is independent of whether part 100 is defective. And assuming the process stays the same from one batch to the next, individual batches should all have the same ratios of results. So this is the way I approach these, right? Now that I know it's a binomial probability, I go to my formula. Probability of X equals N, choose X, P to the X, Q to the N minus X. And what I do is I write down all my variables, right? There's N, X, P, and Q, and then I go back to the question and I read it through and I pick out all of the values, right? So let's see, the number of trials, that is the number of parts that we're selecting, right? So that's going to be 3. We're looking for the probability of a certain number of defectives. So let's actually add that up here. A success in this scenario is part is defective. Remember, I know this is a little counterintuitive, but in statistics, there's no judgment to this, right? Success just means what we're looking for, regardless of whether it's a good or a bad outcome. So the number of successes, that's going to be the number of defectives that we're looking for. That's 2. The probability of a success, remember, a success is a defective part. The probability of getting a defective part is 0.1. And Q is always 1 minus P, so that's 0.9. Right, so now I'm just putting these numbers into my formula, right? This is 3, choose 2, times 0.1 to the second, times 0.9 to the 3 minus 2. All right, so let's see now. Let's talk about, I know this combination thing is maybe new to some people, so let's take a closer look at this. This is 3 factorial divided by 2 factorial times 3 minus 2 factorial times 0.1 squared times 0.9 to the first. And so let's see, the 3 factorial is 3 times 2 times 1. That's 6. 2 factorial is 2 times 1. That's 2. 3 minus 2, that's 1 factorial. And 1 factorial is just 1. Right? So, and again, 0.1 squared, 0.9 to the first. And now let's just go in your calculator. Right, my calculator tells me this is 0.027. So there's my probability. All right, so let me give you one. Right, give you one to practice with here. Give this one a try. See what you come up with, then we'll go over it together. Right, so first, I'm looking for the probability of getting a certain number of correct answers. So that's going to be a success. A success is answer is correct. All right, now let's look at our other variables, right? First, sorry, just for by way of confirmation, this is a binomial distribution. You're randomly selecting your answers, so your choice for question 1 doesn't affect your choice for question 10. There are only 2 possibilities. Right? Either you get the answer right or you get the answer wrong. And because you're doing this randomly, doesn't matter if you take the test at noon or at midnight, right? You're going to be using the same process. So let's see. N is the number of trials. That's going to be how many questions you answer. There's 44 of them. X is the number of successes. That's the number of correct answers. That's 31. P is the probability of getting a correct answer. Well, there's 4 responses. One of them is right. Right? So the probability of success is 1/4, or 0.25. And Q, the probability of failure, is 1 minus 0.25. That's 0.75. All right, so now we can go to the formula. P of 31 is 44, choose 31, times 0.25 to the 31st power, times 0.75 to the 44 minus 31 power. And now again, right, we're going to go to the calculator. This is 44 factorial over 31 factorial, 44 minus 31 factorial, 0.25 to the 31st, 0.75, 44 minus 31, that's 13. And now really go to your calculator. Calculators these days will do some pretty large factorials. Obviously, it's not, 44 factorial is huge, right? And your calculator isn't going to be able to display a number nearly that big. It doesn't have enough digits, but that's okay, because internally it is holding on to the exact value. So when you go and you ask it, what is 44 factorial divided by 31 factorial times 13 factorial, it gives me the answer. I'm not going to write it down here. It's let's see. I've got it on my calculator here. If I do commas, it's 51,915,000,000. It's a massive number, right? So just stick to doing this on your calculator. Right, now that I've got that number, I'm going to multiply it by 0.25 to the 31st times 0.75 to the 13th, and I get an enormously small number. My calculator actually had to go to scientific notation. This is 2.67 times 10 to the negative 10th. There's my probability. So now I want to look at a slightly more practical problem, a slightly more complex problem that comes from a practical situation. Let's say we have this scenario where we're working in a lab and we need to test a bunch of samples for a specific illness, and that illness is relatively rare. I mean, 0.006, that's less than 1%. Right? So it's relatively uncommon that we're going to get a positive result. So here's the issue. These tests aren't exactly cheap, and I'd like to minimize the number of tests that I have to do. I say here's what I can do in this situation. I'm going to take a sample from each sample. I don't want to use the whole thing. I'm going to take a sample from each sample, and I'm going to mix them all together into one big sample that's composed of a donation from all 24. And I'm going to test that. Right? So my question here is, what is the probability that the combined sample tests positive for the virus? All right, well, let's think about this. When will it test positive? Okay, it will test positive if one sample is positive. It will test positive if two samples are positive, and so on, right? Down to, we're doing 24, so down to all 24 samples are positive. All 24 of these will give us a positive result. So what's the probability I'm looking for? The probability of getting a positive result equals the probability of one positive plus the probability of two positives plus and so on out to the probability of 24 positives. Okay, those are all binomial probabilities, right? Those are all binomial probabilities. I could calculate each of those individually using the binomial formula. I would have to use it 24 times. It's not something I'm really looking forward to, okay? Or we can come at this a slightly different way, right? What I'm looking at here, if I can amend this a little bit, this is the probability of at least one positive result in my mega sample, right? So now what I'm going to do is I'm going to use our complement rule, right? The probability of at least one plus the probability of none is equal to 1. Right, now the probability of none, let me rephrase this, right, in terms of positives, this is the probability of exactly 0. That's a binomial probability, but it's only 1, right? So I only have to use my formula once, right? So first, let me again, just so we're clear, this is the probability of exactly 0 positives. Now let's break this down. Right, I'm going to define a success to be there is a positive result. N is the number of trials. That's 24. Right, the 24 samples that I combined together. X is the number of successes. Well, I'm looking for 0. Looking for 0 positives. P is the probability of a positive result. That's 0.006. Q, as it always is 1 minus P. So that's 0.994. Okay, now let's go to our formula. P of at least 1 plus, and it's this exactly 0 positives. This is the one I'm going to use my formula on. So this is 24, choose 0, times 0.006 to the, make sure I get the right one. So this is probability of a success to the number of successes, so that's 0, times 0.994 to the 24 minus 0 has to equal 1. Okay, so let's see. Probability at least 1. I'm really not going to do anything with this. Just going to kind of float along here. Plus 24 factorial divided by 0 factorial times 24 minus 0 factorial. 0.006 to the 0 power. 0.994 to the 24th power equals 1. Now you can go to your calculator. You might notice there's something a little weird looking here, right? 0 factorial. What does 0 factorial equal? How can you multiply 0 integers together? I don't know. 0 factorial, it's defined to be equal to 1. Right? There are some reasons for that. There are kind of technical reasons, but for our purposes, just remember, kind of take it as a definition, 0 factorial is always equal to 1. So now what do I have? I have the probability of at least 1 plus, if 0 factorial is 1, 24 minus 0, that's 24. This is 24 factorial divided by 24 factorial. That's just 1. 0.006 to the 0 power is 1. All we're left with is 0.994 to the 24th power equals 1. Subtract. The probability of at least 1, which is what we're looking for, right? That in that scenario, the combined sample turn test positive is 1 minus 0.994 to the 24th, which is 0.134. So what is this saying? There's about a 13% chance that at least one person was positive, which means there's in the neighborhood of an 86% chance that no one was positive. And that's a good thing for me as the person doing the test. That means 86% of the time, this is going to give me the answer that I need. Everybody tested negative. And it's only 13% of the time that I'm going to have to go back and go to the extra expense of starting to test the samples individually. So, but before we move on, there is one more thing I wanted to kind of point out here, right? We could have calculated this probability, the probability of no zeros, without going to this formula, right? The probability of no positives is the same as the probability, let me write it, probability 0 positives is the same as the probability of 24 negatives. And that's just an and probability. That's the probability that the first sample is negative and the second sample is negative and the third sample is negative and so on. And we know how to do an and probability. You just multiply all the probabilities together. And in this case, they're all the same. It's 0.994 times 0.994 times out to 24 times. And that is just 0.994 to the 24th power. So it's consistent, right? In situations where the binomial situation matches up with our existing, what we know about existing probability problems, we're getting the same answer, right? Which is always good to see. Okay, so how about this one? Right, a clinical trial for a new medication finds that the success rate is 98.2%. And in a trial of 200 patients, I want to determine the probability that at most 3 patients experience failure. So here's what I'm going to do. I'm going to define a success to be failure. So always what I'm asked to find the probability of. I'm asked to find the probability of experiencing failure, so failure is a success. So I'm being asked for at most 3, right? Probability at most 3. Well, what is this? You see, this is the probability that x is less than or equal to 3. And that's kind of a problem for me, because our binomial probability formula doesn't do less thans. It does equals. And only equals. And there is no way to rig or manipulate it to get around that. So the way I would have to do this, I would have to say this is the same as the probability of x equals 0, or x equals 1, or x equals 2, or x equals 3, and then treat this like an OR probability. Right? How do we do ORs? Well, we do them individually. Probability x equals 0 plus the probability x equals 1 plus the probability x equals 2 plus the probability x equals 3. So now here, this isn't an at least situation like I had with the last one where I can bring out our complement rule and make my life easier. Here, you really do have no recourse, right? You've got no recourse but to go to the binomial distribution, the binomial probability formula 4 separate times. Right now, I'm not. If you want to do this for practice, that's great. I'm not going to make you watch through me doing 4 instances of this formula. I will write this out though, just in case you want to check yourself. This is 0.0264. This one is 0.970. This is 0.1768, and this one is 0.2139. If you add them all up, this comes out to a little more than a half, 0.5141. So if you're looking to check yourself, right, get some practice in, that's awesome. You can absolutely do that. That would be the final answer. Okay. Now, if you try this, right, remember, just be careful. You were given the probability of a successful trial, where you're looking for the probability of an unsuccessful trial, right? So keep that in mind when you're determining what P and Q are. Okay, that's a little unpleasant, right? If you have to do a less than or greater than is going to have the same issue. Fortunately, Excel has functions that will do all of these calculations for you. Right? If you're looking to find a binomial probability, this is the formula that you would use, binomial distribution. So if I'm trying to find P of x equals something, I would go to this one. And here's the cool part about this formula. If you want to do P of x less than or equal to A, right? That's what we're trying to do in the last one, P of x less than or equal to 3. This formula will do that for you as well. Most of these input parameters are self-explanatory. It's this cumulative one here that is your new best friend. If you want to do P of x equals a number, put false here, and you would literally write it like that, just no quotes or nothing, just write in the word false. And if you wanted to do P of x less than or equal to A, then you would enter true. Okay, this next one, if you want to do a range, if you want to do a between, right? If you want to do the probability of A less than or equal to X less than or equal to B, then you can use this range version, and you're going to put your A in here for the minimum number and your B in here for the maximum number. Right? And finally, if you want to go the other way around, right? Let's say you know the probability, right? You know this P that I've been calculating, and you want to know the number of trials that will give you that cumulative probability, then you can use this inverse, right? Think of inverse as going the other way. So use this one when you know P and want X, right? X is the number of successes to get that probability. Okay, so now they've got a bunch of examples to work with, kind of think about. In the next lecture, will be the last one on binomial probabilities. We're going to talk about how to find the mean and standard deviation for a binomial distribution. And that's going to let us answer that question we always seem to cycle back to. How can we determine if a given result is unusual or not?